That one.
Hi, I'm Jesus Mata.
Hi, I'm Mrs. Garza.
Hi, I'm Roxana Moore.
I'm Mr. Leal. And I'm Mr. Reyes.
And please don't try this at home.
Please.
Hi, I'm Ashley. I'm a senior at Harlingen South.
I'm Justin. I'm also a senior at South.
I'm Joe, and I'm also a senior at South.
I'm Isaiah, and I'm a junior at South.
And I have a question for you guys. Have y'all ever wanted to light up your principal?
We're your math teacher.
Or your science teacher.
On fire. Well, here we go.
Don't mind her.
Hi, my name is Roxana Moore, and welcome to the 10th Annual Science Day. I'm so glad that y'all are here. I have some very special guests to introduce. They're our biggest advocates for Science Day, and without them, this couldn't be possible. So here I have Mr. Conway. He is our resident Netflix star, believe it or not, but he's our AP Biology dual enrollment teacher. And then we also have our leader, our captain of our ship, Mr. Reyes. So please help me in welcoming them.
All right, welcome to the 10th Annual Science Day. We're really happy that you're here. And I'd like to give a shout out to all the fifth graders that are listening in. And we are very anxious for you to wind up here at our high school so you can do some of these really neat things in your science class. And now to Mr. Reyes.
Thank you, Mr. Conway. So to all our HCISD students watching right now, you're in for a real treat today. Our high school students have put on a lot of great experiments and a lot of great shows for you all to watch today. At the same time, we hope you have some fun. We hope you enjoy the video today. We hope you enjoy these opportunities. These are students doing real videos and real experiments in real time. And so our students have had a blast putting them on. It's going to help you prepare for your exams. And more importantly, I think you're going to have a good time while you're learning. Hawks up.
Hi, everybody. I'm Mr. Mata. I'm here. I'm joined by and I'm super excited to do our first demonstration. Do you guys like fireworks?
Yeah, I love fireworks.
Are you guys?
Yeah.
Have you guys ever wondered about all the colors that they have? Yeah. So our first demonstration is going to kind of replicate what it's like to look at fireworks. So right here in front of me, I have some salts. These are compound chemicals. I'm going to add something to it, and then we're going to light them on fire, and we're going to make an observation. We're going to look at chemical reactions. You guys remember from chemistry, what are some examples of chemical reactions?
Well, there's some color changes, maybe some heat.
Some color changes, some heat. You remember anything else? Maybe some sound?
Yeah, there should be some.
There could be some sound. Think of fireworks. When fireworks explode, they make loud sounds. So let's go ahead and do this demonstration. If you guys would please help me with the lighting and safety first. I'm going to go ahead and put on my goggles here. A few seconds to go ahead and put this chemical in here. Take this off. Help this out a little bit faster. All right. So we're going to go ahead and light these on fire, and then we're going to make some observations because we are junior scientists today, and we're going to use our eyes to make observations. Go ahead, guys. There we go. Go ahead and put this one. Awesome, fantastic. So if we look really, really carefully, we might make or see some observations. What's some of the observations that we can see from this, gentlemen?
There's two different colors, maybe three.
We have two different colors. What are our colors? What colors do we see here, guys?
Green.
We have green and
Orange.
why? Where are we at? What school are we at?
South.
And that's our school colors. So this is a really great demonstration of what happens during a chemical reaction these electrons are like moving in energy levels, and as they move, they release light, that chemical change or that reaction that I keep talking about. And so we see green and we see orange. Thank you, guys.
I hope you all enjoyed that experiment. If y'all have any questions about it, you can send them to the Q&A chat. And so, just like what those salts were that were being used, we used table salt, copper chloride, and methanol to show the different colors that would be created whenever we lit them up.
All right, so without further ado, we will now conduct our introduction for the rest of today. So everybody, ladies and gentlemen, welcome to the 10th Annual Science Day. All right, that's enough of that. So moving on with today's presentations, that was our flame test presentation.
Yes.
The next thing we'll be looking at is a really cool.
Okay, so we want to know what y'all think of Science Day so far. So
Let's check the chat. Good, cool. Somebody got our horrible rendition of Jurassic
Yes.
Park.
I hope y'all all enjoyed Jurassic Park. It's a great series.
So cool. I'm glad y'all are having fun. I believe right now they're getting set up for the next experiment. They're running
Yes.
over to go get
They're running over to the gym right now. So
set up a cool little experiment with liquid nitrogen.
Yes. That
Do
one's
any
gonna
of you
be really
guys know
cool.
what liquid nitrogen is? Or what's so cool about liquid nitrogen? It's very cold. Yes,
Yes.
liquid nitrogen is actually one of the coldest substances we can get a hold of in a fairly easy manner. It's actually so cold that if you put your hand in it, it'll actually like really hurt your hand almost instantly.
Yes, your hand will freeze and
Like, you know, I'm sure you all remember the freeze that happened. When we went outside and your hands would get super cold and it would feel like your fingertips are freezing, but it takes a few minutes. Liquid nitrogen is so cold that can happen.
instantly. Yes. Okay, so let's see. Should we do a joke?
I think we can do
Okay.
a joke, Joe.
So I know that some of y'all may be kind of tired. So Justin, why is it so hard to wake up in the morning?
I don't know, Joe. Why is it so hard to wake up in the
Well, this is because of Newton's first law. A body at rest wants to stay at rest.
morning?
Okay. So do y'all have any questions about the flame test or y'all? Does it burn you? Did it hurt?
For those of you asking if the flame hurt us, we didn't actually touch the fire. So, but yes, was fire and it would be very hot. So we're now being told that our next experiment's already set up. So we're going to pass it over to our teachers and
Hope y'all
see y'all in a
enjoy.
few minutes.
Today's really cool activities that we have planned for y'all. A little reminder on lab safety. Now, if you look at myself and Mrs. Moore, we're both wearing our lab coats to protect our arms and our clothes in case anything spills on us. We're also wearing safety goggles. Our long hair is tied back just so it doesn't get in the way. And we're wearing pants and closed-toe shoes to protect our feet. Now, are you ready, Mrs. Moore, to begin?
Yeah, let's do it.
Okay, so in honor of our 10th anniversary, we thought we'd start off with a little bit of a party. Now, what do we need for a party?
Some balloons.
All right, well, we're gonna need a lot more than 2 balloons though. So do we have any more balloons?
I believe Mr. Motha said that we had some in this blue container, but
This little container?
I don't see how we can get any more than 2. But
Yeah.
I trust him, so let's just try it.
Okay, so let's see how many balloons we can fit in there. Doesn't look like a lot, but we'll see. So let's see. 1, let's throw that over there. Uh-oh.
I see them in there.
What happened to that one?
Oh, I see that. Oh, that's right. Mr.
So
Motha
cool.
said that he put them in liquid nitrogen, which is at about negative 196 degrees Celsius. So hopefully from your science class, you remember that water freezes at 0 degrees Celsius. So that's super cold, to say the least, right? And Ms. Garza's continually pulling them out. And what do we see down there, they should be expanding out, right? So their volume should be increasing as the temperature goes up.
That's 7.
So cool, and you can see this smoke coming out, so that's a physical change. So the liquid nitrogen is going to a gaseous phase. And oh my gosh, there's still more.
That's already
Okay.
10.
Now, this is definitely perfect for a party.
Looks like we're getting all our lunch.
Oh wow.
So you're saying that as the balloon goes into the liquid nitrogen,
exciting.
it goes through a phase change and it goes, I'm sorry, yeah, phase change, right? It's increasing in size.
Knocked my lab glasses off, it's so exciting.
All right, so we have some flowers here. What do y'all think would happen if we were to put these flowers in the liquid nitrogen?
Well, they should freeze, right?
Right, well, flowers have water in them, don't they? So water freezes at 0 degrees Celsius. So let's see what happens if I put these flowers in there. They should freeze. So we're gonna leave them in there for a little bit. There's a lot of fizzing going on, a lot of bubbling.
You can see all the gases coming out again. That's just a physical change. It's going from a liquid to a gas phase. That's basically because it's warmer outside here. We're at like about room temperature.
So these flowers, if our theory is correct, these flowers should freeze, right? So let's see, let's test it out. You ready, Mrs. Moore?
Definitely.
Okay, so here are our flowers.
So
Pretty cool, right?
cool.
That is so awesome. And so Mrs. Moore is using her glove because these flowers are really cold. And we want to make sure that we don't get any frostbite or we don't burn ourselves. That is so cool.
Neat. It just crumbles. Feels like glass almost.
So that's all the
Super
water that was in the
cool.
flowers froze because the liquid nitrogen was way colder than the freezing temperature of water. Pretty cool, right?
Definitely.
Okay, so what else do y'all think we can put in here and freeze?
A banana, perhaps?
All right, so let's see, a banana. Anything else that we have that we can try to freeze?
And I have a couple of racquetballs as well. We can stick those in there.
So those are normally like bouncy rubber balls, right? So let's put them in here. Close the lid and let's see what happens when we try to take them out. Right, so our banana and our rubber balls have been in the liquid nitrogen. Remember, the liquid nitrogen is really, really cold. So we're gonna take them out and watch what happened to our banana and our rubber balls. So we're gonna start with the banana. This is really, really cold. And if y'all can see, there's even, it started to crack already. Okay, that's how all of the water that was in the banana has now frozen. So this banana is really, really hard. It's solid. So I'm going to go ahead. I'm not a big banana fan. So I'm just going to throw this on the floor. Watch what happens. The banana just completely cracked because all of the water that was in the banana has frozen. So it's now frozen solid. So let's go ahead and go back over here. And we're going to try the same thing with the rubber balls. Want to take a look at this one?
All right, let's start by looking at the properties of the racquetball. So we can see that it's blue. It's also very flexible, so I can squeeze it and it can even bounce, right? So let's check out over here. I've been told that we have some crewmates that are a little sus, so let's see which one it is. Open. All right, so let's take a look at our racquetball that we've placed inside the liquid nitrogen. Remember, that's super, super cold. So at this point, just like the banana and the flowers, it should be frozen. So it shouldn't be flexible anymore like our racquetball that we had here earlier. And so let's take a look at what happens to it when we slam it against the wall over here.
You guys science strong there.
So here we have our frozen racquetball. It's still a little frosty, right? But I can no longer squeeze it. And we're going to take it over there and slam it against the wall to see what happens.
Okay. Also the other.
Right? All right, so the imposter's still among us, but let's take a look at some of these pieces from the racquetball. So we can see here that for one, it's still blue. It still retained that physical property. And you can see some of the frost that's forming on them. But as they start to reach that room temperature, they're going to be flexible and they're going to be pliable again, as we can see here with this piece.
Okay.
All right. So that was a pretty cool experiment, don't y'all think?
Yeah. What was your favorite part, Justin?
I think when they froze the racquetballs.
I'd have to say so too. And in my opinion, I think Miss Moore might have been the imposter.
I think you're right. So I know some of y'all are asking. We did make the chat will be to where you guys can only message us now. There was we got told by our teachers to turn off the chat to where you guys can only message us. But the Q&A is still open for us to answer questions. And what was y'all's favorite part? Feel free to send it to us in the chat. What are the gloves made out of? Ooh, that's a good question that I don't know how to answer. So I'm gonna call one of the science teachers over here.
And Miss Moore is actually going to
She's
bring the
gonna
glove
bring us the
for
glove.
us, so we can show y'all an up close picture of it. Okay.
So these are the gloves. They're Z-Tex gloves.
Yes.
They're space age material. They don't really tell us what's in them. Copyright reasons, I guess.
These could be gloves that
Patent pending.
astronauts might use because they have to deal with extremely cold temperatures in space.
They're super thick. Like my hand isn't that big, but when I put it in here, you can see my finger is only here. There's this much padding.
Yes.
So they're really cool gloves when you can't feel any temperature to them. It's really cool. But we don't know exactly what they're made. Okay. Well, we'll read some. How cold was the liquid nitrogen again? I believe it was
As Ms. Moore said, it was 116.
negative
Negative
100.
100.
Negative 196 degrees Celsius.
Yes. So that is extremely cold.
And to answer how we get it, there's a vendor that comes and they deliver liquid nitrogen to us. They have to be. They have to have I believe they have to have a license to be able to get it though.
So you cannot get it at home.
Yes, it is. Do not try this at home. Liquid nitrogen is very dangerous.
Yes.
Is space colder than liquid nitrogen? That depends. And where you're located in space. If you're within view of the sun,
Then
not so much. Space gets extremely hot if you're able to see the sun. But if you're on the dark side of a planet and there's no sun hitting you, you can freeze depending on the amount of radiation in the area. So space can be colder than liquid nitrogen, but not necessarily.
Okay.
All right, I think our next experiment is set up, so I'm gonna pass it back to them. We'll take some more questions in a few minutes.
I hope y'all.
Hi guys, Mrs. Morgan, back from the gym. I hope you enjoyed this liquid nitrogen experiment. I'm going to show you something else that's pretty cool too. It's called dry ice. Dry ice is just carbon dioxide. Yeah, the stuff that you breathe out. And so I have Isaiah here. He's going to help me out with this experiment. So I have this, it's my bubble contraption, and my kids, Finn and Summer, helped me make this. Quick shout out, of course, to them and their teachers who allowed them to come over in La Feria. So we're going to gently hold this so I don't drop it. And so I have a little area right here, and I have water in there. The carbon dioxide, we're going to pop it in there, and it's going to sublimate. And all it's going to do is going to go from a solid to a gas. So it's a phase change, something that you have already been learning about. And so our gas is going to come out through here. We're going to have a little bit of bubble solution, and we're going to check this out because these bubbles are amazing. They don't behave as they normally do. So think about when you blow bubbles out in your house or at the park. Go ahead and sit. And those bubbles, what do? And I hope you said that they just float away, right? And you try to catch them and pop them. These bubbles are unique. They're a little bit different. And so Isaiah right now is putting in a piece of. It's okay. Yeah, we got you. There we go. We're going to close it up. So we're going to let that come over to the top. We'll eventually get there. We need to put another piece. Let's see. Oh, there it goes, Isaiah. There it goes. We just needed to be patient, right? So Isaiah here is going to go ahead and put the bubble solution here, and we're going to try to capture that gas inside the bubble. There you go. So we see it here. So let's observe what happens. So what are we observing, Isaiah?
It's forming a bubble. Right
Yes,
now.
it is.
And the bubble is really dense. So instead of going up, it's just gonna fall down and hit the surface.
All right. So he's been paying attention in class. So that's awesome. Oh, and it popped right there. Let's try it again. We're trying to get this to, science takes time, but when you get to the final product, it is absolutely beautiful. So hang in there with me. Keep hanging in there. Ah! So let's see. Let's try this solution. And you know what? We may need some more bubble. And you know, the best thing about science is that you can make predictions, you can run your experiment, and you may have to change some things. You may have to change it up so that you get it to work. And that's the beauty about science, is that you stay curious, right? You're like, well, what if I do add more bubble solution? Will it make my bubbles thicker? In this case, yes. So hopefully it'll kind of connect and you're able to see very slowly. You wiggle it and look at what happens. Do y'all have a stir bar? Not stir bar, or a stirring rod? What do you think, Isaiah?
Probably. I think it might be collecting up or something.
Yeah. See, I think Isaiah made a good observation. All of the soap, the Dawn soap, kind of sunk to the bottom. So what does that tell us about the density?
That it's really hot.
It's high, right? Because it sinks. If it's dense, it's going to sink. Thank you, Miss Garza. There we go. We finally got one. Let's see if our mixing changed up our experiment a little bit, and hopefully we get some more. We're gonna probably have to add more dry ice, and maybe if we can get this other one running over here, our backup, hopefully that'll work too. So yes, Ms. Garza, let's go for it. We need some extra hands here. Let's mix this up a little bit more so that we can get the next one going. But essentially what you should have seen with the one that just fell, we're gonna try to get it going a little bit more. Try adding more dry ice, so we're gonna increase that. Let's go, we're in Texas. Let's make it big. Yeah, let's close it back up. Let's put this one over to the side. You're so good. Where are my goggles? It might, yeah. We're gonna have to. This one's gonna work. I think we just need more dry ice. Isaiah, you want to try to catch it?
Sure.
Ah, and you can see it sinks, right? It doesn't float away like the ones that you have, blowing at home that you get at Walmart or the Dollar Tree or something like that. Oh, you almost caught it, but it's so cool because the bubbles just sink because it's more dense than what you would normally have just by blowing into them, right? So we can try to check that out. Let's see if Isaiah can. Ah, there we go. So it kind of bounces and it sinks to the bottom. It's so cool. We changed up our experiment. We still got it to work. Let's see if Isaiah can catch this one with a microfiber towel. Almost, but you can just see it. It just all sinks to the bottom. So again, that density, we're super high and it's going to sink to the bottom. We're going to have a really cool one coming up here in a bit. Oh, almost. You had that one bounce on your arm, though. That was really cool. So we're going to go ahead and cut to Justin and Joseph, and while we head over to the main gym, and we're going to show you an experiment where density is lower. So what do you think will happen? We know if density is high, it sinks. If density is lower, think about it. Put it in the chat if you want to. But go ahead. Thank you, Justin and Joe. You're on.
All right, welcome back, everybody.
Yes, that was a really cool experiment. I hope y'all enjoyed that one.
So I've seen some questions in the Q&A box, mainly how does the bubble form? Well, as Ms. Moore was saying, dry ice is basically frozen carbon dioxide. And when it's mixed with the water in the bottle at the bottom of that the apparatus she had, it turns into gaseous CO2. That flows up through the tube. And when she puts that and mixes it with the soap and the water that she had in that little glass, the CO2 bubbles through it and creates a bubble.
So similar to how we create bubbles, we release carbon dioxide when we blow into like an apparatus. And so the CO2 from the dry ice is extremely concentrated, and you can see that in the bubble. And so that's why it becomes super dense and it eventually falls down and it does not rise up.
We hope that answered your questions.
Yes. Okay.
Ooh, okay. Why is the bubble not freezing if dry ice is cold?
Well, so the dry ice was initially frozen, and the dry ice was initially frozen, and when we placed it in water, it created a gaseous form of the carbon dioxide. It immediately changed to carbon dioxide.
It went from a solid to a gas, which is called sublimation.
And so that gas went up through the tube and eventually went into the bubble, which was created and would fall.
But basically, the dry ice started warming up, and once it got to a certain point, it became a gas again, which is much warmer than it was. Yeah, it's just like when you take an ice cube out of the fridge and put it in your hand, it immediately starts melting. But because dry ice has to be so cold to freeze,
it turns into
that it turns into a gas almost immediately.
Yes.
Why is it bouncy and doesn't just pop? I think that.
Yes. So that's because the bubble, we initially created a bubble that had a fairly thin like skin, I would say. And whenever we added more solution or more Dawn soap to the solution and put it on the top of the apparatus, the solution or the skin of the bubble became thicker, and therefore it was able to bounce, and it didn't break as easily, or pop as easily.
Let's see. How is dry ice made? Dry ice is basically made when Miss Moore just told me some really big words, but basically they concentrate the gaseous CO2, so they filter it out or they get it from a chemical reaction. They concentrate it and they put it in super, super low temperatures, and it eventually turns into something that looks just like ice, so they call it ice.
Yes.
When it's really just solid CO2.
Mm-hmm.
It's a really simplified version. There's a lot more of a complicated version of how it's made, but I don't even really understand it. So I'm just going to go with that one.
Okay.
All right. I think they're set up in the gym for the next experiment. So I'm going to cut to them.
Yep. Hope y'all enjoy.
Hello everybody, I'm Jesus Mata, and today we're going to be doing a really cool demo with this newspaper. We're going to see what happens to the air inside the newspaper as we heat it up. Now, in order to do this, we're going to go ahead and we're going to light the four corners of this newspaper, and hopefully, if you guys are excited enough like we are, we can actually build this newspaper to go up in the air. Are we ready, guys? Yeah. All right, let's get it going. All right, let's will it. Come on. I think this might actually work. Let's go. Let's go. Let's go. Up, 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 and yes. So what's happening here is that the air trapped inside begins to warm up, and as it warms up, the density begins to fall, which means that it's going to have less density inside the newspaper than around it, and that allows it to give it lift, and it goes up into the air.
Super cool.
Awesome.
Love it.
All right.
I hope y'all enjoyed that demo. That was really cool. What did y'all like about the demo? Did y'all like the fire, or did you like that the balloon eventually rose up in the air? Or not the balloon, the newspaper.
Yeah. Same principle as how a hot air balloon works. The gas inside got hot, actually expanded, and it expanded.
Yes.
And it went.
And it starts to
the
float.
density became lower than air.
Yeah. became lower than air, and then
It became
eventually
lower than air,
rises.
so eventually it rises.
Yes. Let's see. Deal.
Let's see. We'll be taking any questions if y'all have questions. We're checking. Are getting a lot of questions from y'all, which is great because y'all being inquisitive is awesome. But
So.
what happened to the newspaper is eventually it did just burn up. The fire
Yes.
did consume it. But I think we'll take one more question, and I think they're almost about ready with the.
Yep. They're running back from the gym right now.
And how did it not burn the roof? Well, it burned up before it got there. We did it in
Yes.
our big gym, and our big gym's got a pretty high ceiling,
Yes.
so it.
And the
should be
fire
all right.
eventually dissipated, and so did, or the fire on the newspaper dissipated, and it came back down.
All right. I believe our next experiment's set up, and it's going to be a pretty cool experiment with
The Van de Graaff.
Van de Graaff.
Yep.
Isaiah, it was such a long run back from the gym.
Yeah.
What a demo that was, right?
Yeah.
Well, that was fire, right? And you got to see how fire can make air rise. Now I'm going to show you something electrifying with electricity. So this apparatus here, this very tall column with the sphere on top, it's called a Van de Graaf machine. And what it does is it's kind of like a treadmill. You run this treadmill vertically through this Van de Graaf, and on the very top, the copper comb produces a lot of static electricity. We're first going to see if we can get the static electricity to go into these ribbons up on top. And let's see what the electrons do once they touch those ribbons. Isaiah's going to help me with this one. Go ahead and lift the one. That's going to keep us safe to not get shocked from this static electricity. So I'm going to go ahead and turn on the machine. And as the static electricity builds up, we should start to see these stripes rise on the top of the Van de Graaff. It takes time to build up static electricity, so we have to let it run for a little bit. The orange strand seems to be coming up a little bit, not so much. Let's try that one more time. Isaiah, can you go ahead and use your wand on the orb? Let's see if it's building up static. Very weak. So what we're going to go ahead and do is troubleshoot, because in science, not everything works out perfectly. Let's see if the copper is not exactly touching the treadmill. Get a little bit closer and troubleshoot it. Let's see if that fixes the issue. All right, let's try this again, Isaiah. Second time's the charm, right? Yeah. Let me see the wand real quick, Isaiah. It's very weak. Oh no, ladies and gentlemen, we're having some technical difficulties with this Van de Graaff. Let me see one more time, Isaiah. I do apologize for our students. We do need to get this working correctly for you all. Let's try this one more time. You see, this copper comb has to be touching this treadmill thing, or it's not going to work. If it's even off by a millimeter, we're not going to get that static. Let's try this again. Third time's the charm, Isaiah.
Yep.
Goodness. What a shame. You see, it's building up static electricity, but it's not building it up like it's supposed to. It's only building up a little bit of charge. I don't know why this is happening. Oh no. I'm going to try one last time. If I can't get it troubleshooted right now, we'll come back towards the end and try this again. I am sorry, Isaiah, to make you stand there. I know it's tiring.
It's
From the long run that we just had from the gym.
yeah.
Crazy, right?
Practically exhausted.
Well, you could recover your breath already, Isaiah.
Yeah.
Puts it forward. Let's see. This will be our last go. If, again, we can't get it functioning for some reason or another, we're going to try again a little bit later. Oh, okay. It's building in a little bit. Let me see if I can adjust it so y'all can see it at least. And then we're going to try the Python. It's really, really weak. It's supposed to have a lot more oomph to it. I don't know if y'all can see that it's attracted to my wand, but the electricity is flowing through this, but it's just not building up the static like I'm used to. Let's see if it will at least do my Python demo successfully. Okay, Isaiah, let's see if we can get our Python to fly on its own. At least one Python. For some reason, the Van de Graaff just isn't getting the juice that it needs. If this doesn't work, we're going to go back to the team and we'll have to see what happened. We're going to have to go in the back and try to see what's wrong with this thing. All right, so we're going to go back to the commentary. I'm going to take this to the back and really see what's going on with it. I do apologize. It was functioning yesterday. I'm not sure why it's not playing with us today, but hopefully we can get this resolved as soon as possible. Back to the.
All right,
Okay.
so now you're back to us.
Well, sorry that did not work. We're gonna show it later when it starts working, but of course, in science, not everything works, and that's what makes it science. You have to experiment over and over again, so then you can eventually succeed or make something happen. And so,
Yeah, experiments don't always
Yeah.
work, and sometimes you just have to keep trying. You have to adjust little things like we did earlier when we had the dry ice bubbles. The solution wasn't quite right, so they had to adjust it in order to get the bubbles to bounce. But they're going off to go troubleshoot it, and hopefully soon we'll be able to have that experiment working. But while they're getting the next one set up, we do have some we
trivia.
can take some questions, or we'll actually, I think we have some trivia.
yeah, we can ask y'all some questions since y'all are preparing for the star. Okay, so first question. The Earth has 3 layers of varying temperatures. What are its 3 layers? So y'all can answer this in the chat, and we'll be able to see it directly. Yeah. So it's gonna be all 3 layers.
Yeah, you got to name the layers again. We've seen
Yes.
one. We've got the core. Talking about the Earth's composition. So we've got the core.
Oh,
I
I do see the correct
mantle
answer. Yes.
and the outer one. What is the outermost layer? It's the layer we live on.
What is it called?
The crust.
There
Good
we
job,
go, yes.
everybody. Cool.
Okay, Justin, do you have any science jokes for them?
Actually, I have a pretty cool little fact to tell y'all.
Okay.
Did you know that a cloud, Joe, can weigh up to 1,000,000 pounds?
Oh my goodness, that's massive.
It's all of the water in the clouds, because you don't think about it because you think they're so light and airy, but all of that water, even though it's in a vapor form, there's so much of it that it can weigh up to 1,000,000 pounds.
I guess that's why they say when it rains, it pours, because it literally does. Okay, we can ask another question for y'all. Okay.
Go ahead.
What part of the plant conducts photosynthesis? That's a good question. Okay, y'all can send your answers in the chat. Yeah. I do see the correct answer in there.
Oh, it said you cut off. They say you cut off. You want to repeat it?
Okay, my bad. What part of the plants conducts photosynthesis? So y'all can put the answers in the chat. I do see the correct answer. The correct answer is the leaf or the leaves. They conduct photosynthesis, so they take in light from the sun and then they turn it into energy. Okay, so we're gonna continue. If y'all have any other questions about the dry ice experiment or kind of what was happening in the Van de Graaff, you can put them in the Q&A box. So deliver.
Hey, Joe, got a joke for you.
What's the joke, Justin?
What kind of tree can you fit in your hand?
I don't know, Justin.
A palm tree.
Wow, we have a lot of those actually in the valley.
Yes,
So.
yes, we do.
Okay. How does the static form? So the static forms from the belt hitting the copper, and so all that energy from the belt hits the copper, and it just forms the static electricity.
It builds what's called a static charge. So there's the electrons end up getting kind of freed from the thing, just creating this ball. Imagine it kind of like a ball of electricity around the metal sphere.
Okay.
You know that feeling when you go down the slide on a playground and the hairs on your arm or your legs start picking up, or the hair on your head does? It's that, just on a much more concentrated field.
Yes. And it has to have a lot of movement in order for the static electricity to build up, and that's what the belt is there for. Okay.
Is copper a conductor of electricity? Yes, that is why we use the copper for the belt. That way the charge can actually build on the copper,
and
because copper is the conductor.
The static electricity can be held within the copper. It's actually a very good conductor, and so we use it for a lot of experiments.
Copper is in also a lot of wiring in both in phones, computers, the walls of your house, all over the place.
Yes.
How come we shock people when we touch them? That is the buildup of static electricity. Basically, the charge wants to be released. So eventually, when you hit somebody that has a different charge from you, like if I had a buildup of static electricity on me, Joe did not, it would want to transfer between us, which is why you see that little spark jump from me and him.
It wants to transfer because it wants the charges to be equal between the two of us.
Okay, so we finally have an answer about why the machine probably is not working. So I know it's kind of hard to tell in here because you guys are only seeing us on Zoom, but it is super humid in here.
Yes.
I know some of y'all were poking fun at me and Joe earlier because we're looking a little red, but it's a little warm and very humid in here, and that machine has to be dry in order for the static electricity to build.
Yes.
If you notice, if it's just rained outside, you're not going to be shocking people. It's only when it's been super dry for a couple of days that when you rub your socks on the carpet or you slide down a slide, you build up the static electricity where you can shock somebody.
Yes. And the reason why it's humid in here is the power went out at school yesterday, so we did not have power. Yes.
I did not.
We did not have power in the afternoon, and so the power just came back on this morning, and it's humid outside. So.
All right, I think they're telling us that our next experiment is set up, and it is going to be called the Woosh Bottle.
Y'all will really enjoy it.
It's really cool, but make sure you have your computer audios on because you're gonna want to hear this.
Yep.
But, you know, and Ms. Garza's been here for about,
They're saying they can't.
7 years now.
7 years?
Yeah, it's working now.
Oh, okay,
So,
okay.
yeah.
So we've known each other for a while, and sometimes, you know, we don't always get along. And that's sort of like this next experiment. Sometimes when siblings don't always agree, they kind of make interesting noises. And so we're going to go ahead and we're going to look at these chemical reactions, and we're going to see which one can make the biggest noise or the flashiest fire. Let's go with that, yeah? Okay, so we're going to go ahead and shake a little bit. Make sure that mine's kind of going, ladies. Just make sure that we have enough coating. All right. Remember, sometimes experiments don't always work. Sometimes we don't always get it right, and that's why we try, and try. All right. All right. Let's go ahead and light these guys up. Yeah. mine's pretty much ready. All right, let's go ahead and we're gonna try this. All right, so I'm gonna try this very first one. We're gonna see how this one works. Let's see. Okay, I see it going down. And I think it just might have stopped. Uh-oh. Okay, so the first one wasn't very good. It didn't seem like it wanted to. Let's try it in another way. Let's see if we can, let me see if we can go ahead and light it on the inside. And if you know, it's going. If you pay really close attention, we see the reaction going. And it's not very exciting. It didn't really look like it wanted to do. It didn't want to play. All right, let's try the next one.
All right, so now it's my turn. Let's see if this one works out. All right, guys, so those of y'all watching from school, make sure y'all send us a good vibe so that way we can see if this one will work out. Try with the splint now, see if maybe putting the splint in there will work a little better. Just
No.
completely went out.
No. Let's try one more time with the third one. Oh, look at that one. Ooh, that was really cool. That was real nice. So what could be possibly happening is that right now this room is very humid. It's very hot, and some of our chemicals aren't reacting very well with the extra heat. But normally what would happen is the whole entire bottle would turn on fire. And this bottle did. This bottle actually turned on fire on the inside, and now we have evidence of a chemical reaction. Ms. Garza, would you mind touching this?
It's very hot.
Yeah, and Ms. Moore, I know you have a mask on, but we still have evidence of a chemical reaction. I can sense it. We're whopping. This is a technique that we do when we want to smell something, but we are not sure, and it kind of has a funny smell to it.
Yeah, definitely.
So this is another example of a chemical reaction, okay? And then the last example of the chemical reaction is if I pour this out, we emptied this. This was empty. And now I have a whole bunch of water coming out. So that is another sign of a chemical reaction. All right, guys. Thank you guys very much.
As you can see, there were multiple chemical reactions that just took place. Unfortunately, the humidity in the room did cause them to be a little bit less effective because the water in the air kind of added to the reaction. That didn't make it as effective as it could have been.
Normally it makes a much louder noise. I have no idea if you all were able to hear it or not, but it makes a noise that I think Miss Moore should be very familiar with, being that she is from A&M. I'll let her go ahead and say it if she wants to.
Yeah. Am I on there?
Yes. Normally makes that noise. For those of you who are A&M fans or have family that have gone to A&M, that is should be a very familiar noise to you. But Ms. Moore here is an Aggie, so that is probably why hers worked. At least that's my opinion on it. So we're gonna keep reading some questions while they're getting the next thing set up. Why didn't the fire burn the plastic? Basically, it burned away so fast it didn't have time to catch that plastic. That plastic is very thick and a special type of, I think it's a kind of treated plastic, where it does burn, but it takes a fair amount of concentrated heat for an extended period of time to actually get it to light. Yeah. So it was basically just the fire burned away so quickly that it wasn't going to burn the plastic. So 2 questions. How is it wasn't actually water inside. I believe it's a type of alcohol that they pour inside the bottle. It's a mixture of a couple of different things.
Yeah, so
alcohol and water. They swish around the bottle and they coat all the inside of the bottle. So that's why when they drop the spoon in, the fumes that are released from it will ignite and make that sound. The sound is created because it's a chemical reaction. As we said earlier, sometimes chemical reactions make sounds. In this case, the sound is multiplied by the shape of the bottle to where it only comes out one end. So that's why you normally hear the whoop sound.
Yes. Also, do not try this at home. This can be a very dangerous experiment.
The water came back because the chemical reaction mixed with the oxygen in the air, and just part of the reaction is some of the products that were left over were water. So that's why when Mr. Mata poured the bottle out, he got some water in his hand.
It's a combustion reaction, so it produces carbon dioxide and water.
See, Joe, we remember our chemistry.
Just a little.
Does it work with different jugs? I would imagine so. We usually just use this jug because it's a fairly large container that's easy to whirl around in, but I'm sure you could do it it would work in more than one kind of jug. But again, don't try this on home.
Because it is dangerous.
It is dangerous. It does have fire. Let's see. Do we got anybody have any other questions?
If not, we can go to trivia once again, guys.
Yeah, I suppose, Joe. So you got some more trivia questions for him?
Yes, I do. Okay, Justin, who was the scientist to propose the 3 laws of motion?
Let's see. I think his name was Isaac. Can y'all help me? What do y'all got in the chat? Newton.
Yes.
Good job.
Good job, guys.
His 3 laws of motion.
Okay, so Justin may have some jokes, or he might have some good facts for y'all to read.
Let's see. Ooh, I have a little bit of a fact about tectonic plates. I know y'all learned about those this year.
Shifting.
So, did you guys know that the island of Hawaii actually moves towards Alaska 7.5 centimeters each year?
Yeah, wow. That's a really small distance.
So in a really, 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 really long time, Alaska and Hawaii may end up being part of the same landmass.
Yeah.
Something to think about. Yeah, it just kind of puts into perspective the geologic timescale. None of the tectonic plates move very quickly. They all move extremely slowly over millions and millions of years.
Yes.
I believe we are being informed that the next experiment is ready. Are you all ready to sacrifice the gummy bear?
Yeah.
Okay, everybody. Have you ever wondered why your parents tell you do not eat candy late at night? Well, I have this gummy bear right here. And really quick, we're going to go over the physical properties of this gummy bear. Kind of squishy, kind of stretchy. It has a great smell to it. And it probably has a lot of sugar. And sugar is some amazing stuff. Don't ever really think about how much energy is involved in sugar. Well, we're going to find out that question, or that answer to that question today. We're going to go ahead and we're going to find out how much sugar is trapped in here. Now, why your parents say don't eat candy before bed. So right here we have Mr. Liao, and he's heating up some chemicals for us, and we're going to go ahead and we're going to drop this gummy bear in this test tube, and we're going to see how much energy is released from this gummy bear. Yeah? Yes, sir. Oh, and he fell out. And we saw what happened to the gummy bear. Let's see if we can get more from this gummy bear. We saw a lot of light come out, and that's a sign of a chemical reaction. But we're going to go ahead and we can see if we have more energy left in this gummy bear. Look how much energy is being released in the form of light inside this gummy bear. We can see it violently react, and we can see all this gas coming off, which is another sign of a chemical reaction.
Okay, so that was pretty cool, right? Shows you how much energy is really in some of the food you eat.
Yeah.
And I know I saw it in the chat. Somebody was talking about the sugar. Yes, the the energy is contained within the chemical bonds within the sugar, and when it's burned, all of that energy is released into fire, which is all that bright light you saw, all the smoke
Yes.
coming out.
Mhm.
And there was also, did you guys hear the sound?
Yeah.
Chemical reaction. And we've been saying chemical reactions
Mhm.
can't make sound.
Yeah. There was no more gummy bear left after that either. So
I think Mr. Mata
Mr. Mata
is
couldn't
very
eat
sad.
it. Yeah.
He's very sad about the loss of the gummy bear, but he will do it for science.
Okay. Are there any questions?
He's saying, they're asking, how did you not burn your hands, sir?
How did I not burn my hands? As being a science teacher, before we do any science experiment, we practice and we watch, and it comes with experience.
So he basically, well, Joe, I'll
yeah.
let you take it.
So he pretty much said practice makes perfect. So he's done that experiment so many times that he has perfected it, and he does not get burned whenever he does it.
And I had some really good teachers.
Yes. He also had some really good helpers who made sure that he wouldn't get burned or anything would land on him.
All right, we are being requested to say another joke. So, Joe, do you have one or you want one of mine?
Why don't we hear one of yours, Justin?
I got one more. This one came directly from Mrs. Moore. So, Joe, how do you make a tissue dance?
I don't know, Justin, how?
You put a little boogie in it.
So if you want to make a tissue dance, you can blow your nose. That would be pretty interesting. Oop, I think Justin just dropped.
I dropped my pen. I do
Yes.
that a lot. So I know some of y'all probably heard that one, but that's it was kind of the last of my jokes. So we'll make sure we get more in when the experiments are going on, so we can keep. I know I've been appreciating some of the jokes y'all have been sending us. We haven't been able to talk about them, but
Yes.
we do appreciate them.
Yes.
Thank you.
We hope you enjoy our jokes. But they're very funny.
I think they're getting the next experiment set up, which I think is
The mom demo.
the mom demo.
So
I think
yes.
it's going to be a pretty cool little experiment if it's the one I'm thinking it is. So I will go ahead and let Ms. Moore and Mr. Leal take it away.
Hey guys, this is Moore and Mr. Leal here. We're like the rainbow twins today, and it's a perfect demo for this. So you saw all that sugar that was contained in the gummy bear, and if you're like my son and daughter, they can pack that away. They say they have a food stomach, and then they have like a dessert stomach. And so what happens there? And then their tummy starts to hurt. So we have this awesome experiment called Mom to the Rescue, or maybe Mr. Leal to the Rescue. So what we have here, we have a beaker, and we have milk and magnesia, Mr. Leal.
Milk and magnesia.
So what is this used for?
Usually it treats sour stomachs. Usually when you have a lot of acid in your stomach.
Ate too many gummy bears, perhaps?
Ate too many gummy bears, too many sharks like my nephews eat, or those little fruit roll-ups that my niece likes so much.
So it's this lovely white liquid stuff that you're probably like, no, Mom, no, I don't want to. Or maybe your grandma's giving you some, or you know, the adult that helps you out at home. So we have our milk and magnesia, again, like Mr. Leal said,
Our mom.
Our mom.
Mm-hmm.
We have this cool stir ball right here. It's a magnet, and I know y'all learned about magnets back in your 5th grade classroom. And there's another magnet here in this hot plate. And so we're gonna put this in, and what it does, it's going to make a connection, right? It's gonna be magnetic and
Magnetize and spin.
And we're gonna turn on the stir bar here. We're gonna add, oh, you know what, Mr. Lau, maybe we need to add our water first.
Our water first, yes.
Yeah.
Okay.
Going out of order, we're so excited to say that.
I love chemistry, man, so much.
So this is our medicine. Yeah, that should be enough, I think. And if not, we can always add more. Again, in science, we're gonna troubleshoot and, you know, fix some things up. So usually my hot plate is a stir, and it's stirring. And Mr. Leal is gonna add some universal indicator. This looks really cool. It's gonna match our lab coats here. And so first, we're gonna check it out. And what we're going to see is a little bit more, Mr. Leal.
Okay, you got it.
All right. A really dark purple color. So these indicators detect whether it's an acid or a base, and you're probably more familiar with acids if you've ever had a lemon or a lime and you're like, wow, that's sour, that's an acid, right? And so if you have a sour stomach, we're gonna use this medicine and we're gonna have, this is vinegar, and if you love pickles, then you probably like vinegar too. You like that tart taste.
Anything sour.
Yeah. So if we have a buildup of acid, like Mr. Leal mentioned earlier,
Too much sugar on
we
my
can,
stomach.
yeah, we can use the milk of magnesia, in order to kind of neutralize it, kind of even it out and make our belly feel better. So let's check it out. Let's see what happens. Whoops. Oh, we see it change colors and it goes back to purple. Oh, then red is going to be red.
Oh my goodness.
Nice
Miss
orange color. And it's turning green? Back to blue?
Where are we at on our lab coats? We're going
I
down.
think, yeah, I think we're
Feel
going
like
down
here.
in our lab coats. Let's bring it back up. Let's see what happens when we add a little bit more vinegar. Oh, so here we are. We're going toward the orange. Oh, we're heading to the
Middle.
green. And then we have our blues and our purples at the bottom, the whole spectrum, right? So this
Yeah.
kind of continues on until that acid in your stomach has fully reacted with that medicine that your mom gave you. So we're trying to get it to a nice green color so it's nice and leveled out and your belly doesn't hurt anymore.
When it's about green, that's where you're going to be comfortable. When it's not too acidic, but not too basic either.
So where are we at here?
We're a little bit too basic still. It's like a blue to a purplish. We want it to be green.
And red is no bueno either. That's too much acid, belly hurts.
That's why your parents should be the only ones to give you the dosages so you get the right amount. If you get too much of this, it can cause problems too.
Yeah.
And as you can see, even with all this acid, we still have too much of the mom in play here.
And we can do that over and over until all that acid starts to react fully with that medicine.
Eventually, what should happen is that the medicine inside the container should eventually neutralize with the acid in your stomach, giving us that green color. But if it keeps staying blue, that means that we added too much milk and magnesia to the acid that we're adding
And
to
a
it.
good example of why you shouldn't take medicine when you don't need it. If you don't need it, there's no point in taking it because it's gonna just be blue. So, and again, like Mr. Blair also, this should only be administered by the adult that takes care of you. And I could watch this all day, guys, but it's so cool. It's just gonna go back and forth, back and forth. Just a really cool demonstration. Don't need too many gummy bears. And so we're gonna hand this back over to Justin and Joe.
All right, thank you, Mrs. Moore.
I hope y'all enjoyed that experiment. That one kind of showed like the difference in acid and base and how it equalizes and goes back to neutralization. I would say.
Yeah, to kind of explain how it changes color. So basically, that stuff Mrs. Moore called universal indicator shows how acidic or how basic a
Yes.
solution is. And as they poured more vinegar into the milk and magnesia,
It became yellow.
it
Yeah.
became more acidic. And then as that acid got consumed, it became more basic. And they added more, it became more acidic. And the more acidic it became, the more it became red or yellow and then red. Green was about neutral. And then as it went blue and eventually to that super deep blue, that's the more basic.
Yes.
So that's a real basic explanation of why it changed color. Okay, yes, I have the card for saying the colors now. Thank you, Mr. Yell. So the bright red was a really low pH of about 4. It's super low. It's not as low as your stomach acid though. It's one of the facts I was going to say earlier. So a little bit of trivia for y'all. The acid that's in your stomach, the one they were talking about, is actually strong enough to eat through steel.
Yes. So don't eat steel.
Don't eat steel. We do not condone that.
Yes.
But the acid in your stomach can eventually eat through steel.
Yes, it'll be able to break it down. So if y'all have any questions,
Yeah, we'll be taking questions while they're getting the next experiment set up. I think they're getting it set up in here, and I don't think they're headed out to the gym. So
also, if y'all were wondering what was stirring that solution, there is a magnetic stir rod at the bottom, placed at the bottom of the beaker, and it attracts to the hot plate, and that allows the magnetic stir rod to spin, and they don't have to stir the solution together. It automatically stirs it together.
for those asking if that's the only color, the color of the universal indicator can go from red to orange to yellow, then to a light green, a darker green, blue, and if it's super basic, it'll turn purple.
Yes.
So universal indicator is really cool, and it's used in a lot of experiments actually. I suppose we can do a piece or two of trivia before we go on to the next thing, because we are getting a lot of requests for trivia. So, Joe,
Okay, so
Trivia Meister.
if you did not know this, bananas are radioactive. So bananas contain potassium, and so potassium actually decays very slowly. So you don't need to worry about eating bananas because potassium decays so slowly. And so if you want to know how many bananas it takes to be poisoned by or radioactively poisoned, you'd have to eat 10 million bananas at once to die of radioactive poisoning. So don't worry, bananas will not harm you. But it's kind of an interesting fact that bananas are radioactive. Justin, do you have anything?
No, but I do want to answer one of the questions that I got asked. Why did they want the color green? The green is the pH of 7, which is approximately neutral. It's about the same pH level as water, as
Yes.
normal tap water. So that's the one that won't hurt your stomach. It won't upset your stomach. So that's why they were going to try to get to green. I know they kept adding acid, which would make it go past or go lower than green. And then as that was consumed, it would go back to blue. But once they eventually added enough, it would go back and forth, get smaller and smaller, and eventually
Yes.
just land on green. Hope that answers your questions. Okay. Well, the YouTube chat seems to be requesting one joke. I think we can oblige, and they are telling me the next experiment's ready. So, Joe, what did the tree wear to the pool party?
I'm not sure, Justin.
Swimming trunks.
Oh my goodness. It's a good joke.
All right. We're going to pass it on to the next experiment, which I hope y'all will enjoy.
All right, guys, so Mrs. Garza here, and I'm joined again by Isaiah. Now, before we close it out, because we've had so much fun with you all this Science Day, we hope you all have enjoyed it, but I have one last demo for you all. Now, if you can see, I found this magic genie bottle, right? And so before we close it out, we know that y'all are going to be taking your STAR test soon. So we want to see, what are your wishes for the genie? Go ahead and type those wishes in the chat. Isaiah, what are your wishes from this genie bottle?
Well, one of my wishes from this genie bottle is that all the fifth graders taking the STAR test to pass it, because I know it's a very difficult test for some fifth graders.
I know, right? So let's go ahead and see everybody getting their wishes in the chat. Okay, so what I'm going to do is I'm going to go ahead and I'm going to rub the magic genie bottle. It does have a cap, so I'm going to go ahead and have to remove the cap. So let me go ahead and give it a nice rub, and let's see if the genie grants our wishes. What's happening, Isaiah?
Well, as you can see, there's some smoke coming out of it, and that is a chemical reaction.
That's a lot of smoke. All right, so that's our genie smoke, right? And it does look like magic, right, with the genie. So this is actually oxygen gas that's coming out of the genie bottle, because what we just had happen in the bottle was a chemical reaction. And if you remember, Isaiah, that's when we formed something new, right? When two things come together to form something new. So what was one of the signs that we had a chemical reaction happening?
Oh, the smoke was one. The smell was another one too.
Right, so
Smell.
there is a little bit of a strong smell. The smoke was that oxygen gas coming out of there. So we have, remember that we can always walk. We have a little bit of a smell too. And if we touch the bottle, I'm touching it very lightly because it is very warm. So we did have that change in temperature too. All right, so we hope, guys, that y'all enjoyed Science Day. We're going to go ahead and we're going to send it over to our moderators, Justin and.
Wow.
All right. So that was pretty cool. I know you could see it from here. It looked really neat. So that was our last experiment for today, but me and Joe are going to be here taking some questions before we go to our closing segment. So feel free to ask us any questions we have.
The Q&A.
We'll put them in the Q&A box. We'll answer as many as we can. Okay, there is apparently questions. So go ahead and ask some questions, and we'll preferably science related, but we'll answer a couple that aren't so science related.
Yeah. Okay. How old are you?
What was inside the genie bottle? That would be actually I think we have.
Hydrogen peroxide was in the bottle, 30% hydrogen peroxide, and
Manganese.
Yeah.
Yeah, it's what you use to clean
Manganese
cuts. I
oxide.
know some of your moms may have used to clean your ears.
Yeah.
Manganese oxide.
Dioxide.
And there was hydrogen peroxide and manganese dioxide were mixed in the bottle and sealed.
Yeah.
And once it was unsealed, all the smoke started pouring out, as you saw.
The
Which
manganese
was not
dioxide.
smoke.
Yeah,
but
the manganese
oxygen.
dioxide was what was added to the solution of hydrogen peroxide.
Okay, they keep asking how old we are. So, Joe,
I'm 17, about to be 18.
I am 18.
Yeah.
Yeah, that's how old we are. Have I ever hurt myself doing a science experiment? A couple of burns, but nothing serious.
Yeah.
And it was, well, I tripped.
Yeah.
Hot plates are hot.
One time, sophomore year, I got something in my eye, and I had to use the eye wash. So that was pretty interesting.
So make sure you listen to your science teachers when they give you the when they give you instructions on how to conduct lab safety.
Yes.
Yes,
Lab
safety is
safety,
important.
yes.
Safety first.
Yes.
Yeah, I know we had gotten some questions earlier about the color changes of the milk and magnesia or the mom demo.
Yeah.
We kind of explained it earlier, but basically the universal indicator is what it basically tells you how acidic or how basic something is. And as Joe has these colors here, the red is more acidic, and as you go this way and then eventually this way, you get more basic. So it started off very basic because milk and magnesia is a basic substance. Yep. As they added the acid, it's shifted over to the acidic side. But as that acid was consumed, it eventually went back to the basic side. And as they kept adding more, the jumps would get smaller and smaller till eventually it would become a neutral substance.
And so the jumps get smaller and smaller because as more acid is added to the base, it reaches equilibrium. And once you reach equilibrium, it'll be a neutral solution.
Let's see. For a non-science related question, yes, I play a sport. I'm on the swim team and I play water polo.
And I played tennis in school and soccer outside of school.
Yes, actually, the colors are used to test the pH of a pool. It's a little different. It's a different set of chemicals, but when you are testing the pH of pool water, you scoop it up and there's this little thing. You add some chemicals to it. I don't remember the name of the chemicals off the top of my head, but it does tell you the pH of the water and how much chlorine is in the pool, which is stuff you need to know because too much chlorine in a pool can be very, very bad for your skin.
Yes, and so they test the pH in order to make sure that the pool is safe.
Mm-hmm. Again, we're getting some question about how to make some of these experiments. Don't try these at home by yourself. If you will do any of these, your teacher would be the one facilitating it. But again, so just don't try any of these at home. I know some of them seem like they're not as dangerous as others, but they still, if you mess them up, they can have some interesting consequences.
Yes.
So I think we'll take a couple more questions, then they're about ready for the final thing. Remember, any questions need to go in the Q&A box, not the chat, because we're not really checking the chat. We'll do it at the end. We'll take 2 more questions, and then we'll answer a very special one that we just got.
Yes.
Where can you try some of these experiments? Once you get up to high school, I'm sure some of these teachers at least will still be here. You can join the AP Sciences, and I'm sure you will
join AP Chem.
Woo!
Join AP Chem.
They will gladly take you into the Science Day preparations. Yes, we are friends, if you haven't guessed.
Yes.
And I suppose to end it off, because we did get a request to do this, Joe, on you.
Okay.
Do that's all we got. So I want to wish y'all the
Yeah.
best of luck on your STAR test, and
I hope y'all enjoyed science
y'all are
day.
gonna do great.
Yeah.
But we'll see y'all on the other side.
All right, guys, we want to thank you guys for being here. We are so just happy to be here. We made this especially for the 5th graders taking their Science Star. You are ready. Your teachers have prepared you. We are also going to send over some mini target lessons that some of our students here helped us produce. And of course, Mr. Torres is behind the scenes making this all happen. Come on here, yes. Yes, he's our MVP. Again, we have Isaiah, Mr. Leal, Ms. Garza, Mrs. Moore, Mr. Mata. Alexis is helping out Mr. Torres today, so he was behind the scenes too. And of course, y'all know, very familiar with Joe and Justin. Thank you guys, and
On behalf of Science Department,
yeah,
good luck and see you
stay
guys.
curious. Keep asking those questions, guys. Thank y'all.
Bye, everybody.
Bye.
Good luck.
We'll see you here at South.
They meet.